So this is f of x. We're supposed to graph the derivative of f of x. What that means is we're supposed to graph every single instantaneous slope. And obviously we can't go calculate every single instantaneous slope, but we can draw them. So at x equals 0, here's my slope. Here would be the tangent line. Actually, we keep following the same path, right? Because at x equals 0, x equals 1, x equals 2, this thing keeps increasing at the same constant rate. It's going up by 2 to the right 1, up by 2 to the right 1. This function doesn't do anything funny. The slopes everywhere are 2. When you have a straight line, then you have the same instantaneous slope all over the place. Right here, we're increasing by 2 over 1. Right here, it's still the same line, so we're still going up by 2 to the right 1. Everywhere has the same slope. So the graph we want is going to be the graph I'm going to draw here in orange. It's a flat line right across it too, because it represents 2 everywhere for the x-axis. Everywhere has the same slope. It has a slope of 2. So we have another graph. This one looks like it's maybe cubic. I was supposed to sketch the graph of the derivative of x by dragging the red points along the vertical direction to adjust the slope of the black tangent lines. Oh. Okay, well, here, I'm going to start with this one. At x equals -2, it looks to be a slope of 0. So I think that's what they mean by the red dot. It says I want to have a dot at 0. That doesn't look to be exactly 0. I hope it doesn't mark it wrong because of that. So really what you're doing is you're just trying to drag it so that the black line becomes a tangent line. So it's just trying to model the graph's behavior at that instant. So this one should have this for a slope. This one should look like this. This one is perfectly leveled off at 0. And this one, slopes look like this. Man, that's the best I can do. I can't get really exact with this. And it likes it. Okay. Yeah, because to help you graph a derivative, you're thinking about all the slopes. Like this slope looks to be like maybe 4. This slope is 0. This slope is like -2. This slope is like -3, -2. Those are the y values on your graph of your derivative. Nope, this is a different question. We're supposed to graph the derivative of this function. So let's start thinking about what's happening with the y values on the derivative. Okay, the y values in the derivative are all slopes. So if you have this, then it means at x equals 2, the slope is equal to, I don't know, whatever this is in my random graph. The slope would be 3. So the y-axis on the derivative is going to be those instantaneous slopes, the slopes that you see at an instant. So let's just estimate some. The easiest one to do is right here at x equals 2. The slope is 0 because it's a perfectly straight line. So in our graph of our derivative for f prime of x, the derivative should have 2, 0, 0 for a slope. And then maybe at x equals 4, this is an estimate, we want to keep that in mind. It looks to be about -1. It looks like it's decreasing by 1 and going to the right 1. And then on the flip side of that, maybe at x equals 0, the slope would be +1, because if you were to draw this line out, maybe that looks like it rises 1, runs to the right 1. So when I choose my graphs, I'd use those estimates to help me pick, but what you should see, 0, 1, 2, 0, 4, -1. It should make a perfectly straight line or something close to it because this is quadratic, and later on we'll learn that the slope of a quadratic is a linear function.